Hi. Hi, I'm Shantanu. I'm here to present my paper at this year's MICCAI. In this paper, we utilize the concept-based interpretable models for efficient transfer learning. Deep neural networks attain amazing performance across many tasks, but they fail to generalize. For example, previous research shows that deep networks are brittle to a new domain due to different scanner types and data acquisition process. Consider that you trained your model on one domain and you want to deploy it to another. Standard technique is transfer learning, where you get the initial model, you obtain the labels, and you fine-tune the parameters on the target domain. But it can be inefficient both in terms of data and computation. However, if we truly learn the clinical rules like the radiologist, those do not change from hospital to hospital. These rules are transparent, thus engendering trust in AI. So we start off with a black box and carve out the interpretable models from the black box to extract the domain-invariant rules. Our first assumption is that the black box is divided into a feature extractor, phi, and a classifier, h0. Also, in the training data, we have the access to the radiology reports along with the images. We extract the concepts by parsing the radiology report via Stanford RadGraph NLP pipeline. The extracted concepts are anatomical landmarks and observed pathologies. So the training dataset consists of these three triplets: the images, the concepts, and the class labels. Remember that we start with a black box model. The idea is that the black box model encodes concepts in its intermediate layers. So the first step is to discover those concepts. So we learn a linear projection from the feature extractor phi to the concept space. These predicted concept values will be the inputs to the interpretable models. So what do we do when we discover those concepts? We find a rule in a form of first-order logic to combine the concepts and mimic the behavior of the black box. However, these rules are usually very simple and work well only for a subset of data. So we borrow the ideas from the so-called deferral model, which are represented here as the selector. The selector is a binary classifier that chooses between the interpretable model and the black box. When it is confident, it uses the interpretable model for the specific data subset. When it is not, then it defers to the black box. Whatever is remained, we refer to them as the residual. We copy over the initial feature extractor phi and optimize the last layer of the black box to specialize for the residual data. It gives another black box and we continue this process. Finally, this G1, G2, G3 are the interpretable models extracted during the different phases of our method. And each of them are referred to as the expert on the specific data subset. Also, there could be a small residual left that will not be covered, and we view them as the unexplainable part of the data. Our first goal is not to compromise the performance of the black box. So we can see that our model here outperforms the concept bottleneck model and the post-hoc concept bottleneck model baselines for detecting effusion. Also, the performance gap with the black box is minimum for our model as compared with the baselines. Same thing is there for pneumothorax as well. Now let me show some examples on the explanations. These 4 images come during the test time. Expert 1 covers the second instance, and it uses left pleural, right pleural, and pleural unspec to detect effusion. However, expert 2 relies only on right pleural and pleural unspec concepts to detect effusion. Likewise, we continue. We can see that different experts focus on different concepts for the specific instances to detect effusion. So let's apply the carved experts to a new domain. However, on the target domain, we may not have the radiology reports to parse. Here is what we do. We assume that we have labels for a small proportion of patients. First, we apply the black box from the source domain to predict the class label in the target domain. We find some of the samples where the model prediction is correct, indicated by green, and for some it is wrong, indicated by red. We look into the concepts extracted for the correctly diagnosed samples. We assume those are true concepts as the rules we extracted will gonna work for those subjects. For the other cases, we don't know the ground truth concepts. Next, we use semi-supervised learning to extract the pseudo concepts for all samples using the correctly diagnosed patients. Finally, we utilize the pseudo concepts and update the selectors and the experts in the target domain for only 5 epochs. Here is some of our results. The x-axis shows the proportion of label data on the target domain varying from 2.5% to all the way to 15%. Gray is the vanilla transfer learning with the black box, and blue is our method. All the other lines are different ablation study. You can see that with much smaller amount of data, we achieve superior performance. Here is the log of the flop count, which is basically says how much computation do we need. The lower is the better. Blue is our method and gray is the vanilla black box. As the experts only use the lower dimensional concepts and the residuals only update the last classifier layer, the overall computation is minimal for our method. The similar results for cardiomegaly and also for edema. Thank you. Please come to our poster session in MICCAI at this particular venue.